Bismillahirrahmanirrahim. In today's class, we will be discussing one of the very important concept of data structures, that is searching. So, as we already discussed within the class, the main idea of the design of data structure is that we should select a structure for data that is efficient in performing different tasks on computer. One of the tasks that is very frequently performed on the stored data and which is related to the organization of the data, or you can say it is directly related to the data structure, is searching. So this searching is often performed on the stored data. So if you have a record of data, that maybe you can say the students the record, or maybe the inventory record, or whatever, in the form of data which is stored in the computer, and then you need to perform frequently one of the key concept, that is searching, to search out some specific contents within the data. So this is really an important task. So we will be discussing this searching concept. We will be discussing what options we have, what are their limitations, and what are their pros and cons. So one of the very basic technique that we can apply for searching of data is a linear or sequential search. So the idea of this search is that if you have a record of data, you have entries, maybe for example you have 100 entries, and the task you are going to perform is to search out some specific entry. Then using linear search, the basic thing you can do it to start from the beginning of the data, keep on retrieving each and every element, and keep on identifying that whether it is the one that you are searching for or not. So if the element you are currently visiting is actually equal to the element that you are searching, then it means that you have found it out. Otherwise, you keep on moving to the next and next element till or you have visited all the elements. So at the end of the search, you may find an element, or you may reach to the end of the element without finding it. So in the both cases, the execution of the linear or sequential search will stop. Uh, so these are the start. So if you are going to implement this algorithm, for every algorithm that is performed, it has some stopping criteria. For linear search, so if you think about it, the stopping criteria can be one of the two conditions, is actually one of the two conditions. The first one is that when you find an element, then you have to stop, because the task you were performing was to find that element and you have found it, so stop executing further the algorithm. Another stopping criteria would be that you keep on searching in element, you keep on moving to next element, and during that operation you reach to the end of the data. Then in that case, of course, once you reach to the end of the data, and even if you didn't find it, you don't have any other option to move on to the next element, so you will stop again. So these are the two stopping criteria that your algorithm should follow. Within this discussion, I will be frequently using the term list. So because list is a very common term, once you say list, then it's clear to every student that it might be a sequence of data or a sequence of something, an organized way of representation of something. So that in order to represent that concept, I might use frequently the term lists. But also list is a specific term for a specific data structure as well. So during current discussion, whenever I'm using the term list, it doesn't mean that list term, but it means a general concept of a sequence of data in a list or in an organized form. So as it might be clear to you that within the linear or sequential search, you keep on moving to next and next element till you reach to the end of the list. So of course, as you may visit all the elements within the list, or you may visit all the elements within of the data. So the order of complexity is order n. Another very important thing is that for linear search, it's not the requirement that the data have to be in sorted order. So if the data is sorted or unsorted, is the concept of the search is to visit each and every element. So if you are going to visit each and every element, even if it is sorted or unsorted, it doesn't matter. So this linear search is not taking any advantage of the sorted form of the data. Now we will just discuss its implementation. It is in fact very simple, but still in the implementation point of view, if we see that uh, if we are interested to write a function which can perform a linear search, then what will be the list of arguments to this function? Of course, the first thing here is an array of items. So we need the list or array or the data actually, in which we will be searching the second argument, which is a key. We have to search it out. So if we are passing the data in the form of a list or an array, you can say, and within the data we have to find that specific element, then we also need its limits, that is the lower and upper bound. So with the help of these bounds within the body of this algorithm, this function, we will limit ourselves to the legitimate bounds of this array, so that we can make sure that we shouldn't get out of the bounds of this array, because in such case, if we do so, our program will terminate. So we don't want our program to be terminated unexpectedly. So that's why we need its lower and upper bound. If you see here, we have passed the array to this function, but we have passed just s with empty brackets, empty square brackets. So if we look at here, we haven't provided any uh, information about the size of the array. So that's why the array we will be passing to this function will be, actually a pointer to the first element of the array. So we will be actually be passing a pointer which will contain the address of the first element of the array, and from that address we will be sure that okay, this is the address of the first element, but we didn't provide any other information to this function through which we can we are in a position to know that what is the bound, what are the number of elements. So that's why we need this lower and upper bound, so that through this low and high elements we will keep track of visiting the different elements within the bounds limit. So that's these are the different arguments we have passed to the function. We have defined an integer I. We make initialize it to the lower boundary. So this I will be used to visit different elements within S array. So this is the actual while this is the loop through which we will be performing the linear search. So through this loop we will be visiting the different elements within the array. So we need to specify the two terminating condition. So if any one of these conditions become true, the loop will be terminated. So as we can see, we have defined conditional AND here. It means even if the first condition become false, the loop will be terminated, or if the second condition become false, it will be terminated. So the first condition is, in the previous slide we discussed, we have two terminating conditions. The first condition is that if the current element is not equal to the key, it means that we didn't find it, keep on moving. So if this condition become false, it will be terminated. We have defined AND, so it means just let me again rephrase what I said, that when any one of these conditions become false, it will be terminated. When both of these conditions are true, then it will keep on executing. So that's the main idea. So if the condition is true and this condition, the second condition, which is that we need to be at the we need to be below the upper bound, and if the element we are searching is not yet found, then we keep on moving to the next and next element. If any one of these conditions will become false, the loop will be terminated, and we will the next jump on to the next statement, that is if statement. So if this loop is terminated, we are sure that one of these conditions are false. So if the first condition is false, it means that the element ith element was actually equal to key. It means we found it. However, if there are chances that the loop may terminate due to the second condition becoming false, which is I is less than high. It means if this condition is false, it means that we have reached to the upper limit of the data or an array, and still we didn't found an elements. So here after the while loop we will check that whether we have found the element or not. So if Si is equal to key, it means the element is found and we are returning the ith index. It means it is the index on which the key element exists. However, if this condition is false, this if is false, it means it's 100% guaranteed that the loop was exited due to the second condition, that was that we reached to the end of the array and still the element was not found. So in this case we will just return -1. -1 is an index that generally doesn't exist in an array. So it will, if this function returns -1, it will provide information or signal to us that the element or the key that we are searching actually doesn't exist. So this all about the implementation of a linear search. The next search is an improved version, which is a binary search. So I use the term improved. What does improve? So what do I mean by improvement? By improvement I mean that it's computationally efficient. It means that if the problem is a searching problem, then it will find the key very efficiently with less number of, while consuming least number of computer or machines clock cycles. So it can within few steps it will find the key. So its name is binary search. So you might already know the term binary. Binary means 2, 0 and 1. So it's something linked with 2 or by. So in the next slide, when I am going to explain this binary search, I will also define this binary or 2 type concept, that why this search was named as binary. The main condition for binary search to apply is that the element or the data that you are going to search need to be in sorted order. So in the linear search we said that for the linear search, it doesn't matter whether the data is sorted or unsorted, because linear search was not taking any uh, uh, advantage of the sorted form of the data. So it was treating sorted and unsorted data in a similar way. However, in binary search, it takes advantage of the the sorted form of the data. So hence, uh, um, and to that advantage, it's computationally efficient. So, in order to explain what the main idea of the binary search is, uh, um, you have to start from the beginning of the data, or you can say that for a binary search, the idea is that you start from the start of the list or the data, as we did in the case of linear search. So the data is organized in a sequence form. You have the start of the list, the beginning of the list, you have the end of the list. And then the task is to find a key within the lists. The first thing you have to do is you have to find the middle of the list or the array. Once you have found the middle element, then you compare the key with the middle element. In the linear search, we used to compare it with the first element and then second and third and so on and so forth. And in the binary search, we used to find the middle of the data and then used to compare the key element with the middle element. Then after every comparison, one of the three conditions might be true. What are those conditions? They are that the key may be equal to the middle element, or if it's not equal, then it may be less than the key, or it may be greater than the key. So one of these three conditions may become true. And if each of these conditions, for each of these conditions, we have to perform a different operation using binary search. So what are those different conditions? So if the key is equal to the middle element, though, then that's it, because that was a task we were targeting, to find the key. So if the middle element is equal to key, it means that you have found the element. Stop. However, if the key is less than the middle element, it means that whatever you are searching for won't be able after the middle element, because we already know that the data is in sorted form, and if the middle element of the data is greater than the key, or if the key is less than the middle element, it means the key will exist only to the left side of the middle element. The third condition was that if the key is greater than the middle element, it means that the key can only exist to the right side of the middle element. So in each of these different conditions, as I said, we perform a different task, and after each of these different conditions, we again reinitialize our limit and keep on performing this binary search on the revised limits of the data. So how? So these different conditions will be explained in a bit more detail using this pseudocode. As I already said, that within the binary search, you have an organized form of data. You have a key to be found within the organized form of data. Within the for the data, you have a lower bound, you have an upper bound, and you will require to find the middle element. The key is first searched with the middle element. You may find a key, or you can say that the middle element may be equal to the key, or the middle element may be greater than the key or may be less than key. And for each of these different three conditions, you treat it differently. What are the differences between the operations of these three different conditions will be explained using this pseudocode. So uh, for the binary search algorithm, you pass the data. Here we refer to the data using keyword list. We define the element to be searched with the keyword key, and then upper bound is specified using keyword upper underscore bound. We have defined index and found to other you can say arguments to this function. So the first thing is that you have to define the bounds of the lists, and you keep on searching for the key. So once you have defined the bounds, which is the first, last, and middle indices within the list, the middle element is compared. If the middle element is less than the key, it means key is greater than the middle element. It means the key can only be found after the middle elements. After this condition, you need to revise the bounds, as the key can only be found at the right side of the middle elements. So you make a new list, which is a sub list of the existing list, and for this, and the bounds of that list will be, its lower bound will be equal to the middle element, and its upper bound will be equal to the upper bound, actually the existing upper bound. And you can revise the middle index by making lower plus upper divided by 2. So that's one of the condition. So either it can be less. If it's not less, then it means it's greater or equal. So in both cases, we will consider, if it's not less, if the middle element is less than key is not true, it means the middle element is either greater or equal to key, or you can say the key is less than the middle, less than or equal to middle element. It means that we have to consider the left half of the existing list, and for the left half of the existing list, the lower bound will be the same. However, the upper bound will be revised to the middle index, and then you keep on doing this until either the list is empty or key is found. So if the key is found, or if the sub list that we are searching for is empty, then we will stop. So let me again explain it with a bit more specific code. Here we defined n is equal to 100. So here the limit we have is from 1 to 100. For the binary search, algorithm, we are passing the different arguments. First and last are actually the bounds. So first for initially, the first will be equal to 1, the last will be equal to the bounds. So which will be the last elements. So we will keep on iterating a loop. So first we have to find the middle index, which is equal to first plus last divided by 2. If the middle element is less than key, it means the key can be found to the right side of the middle element. So in that case, first will be revised to middle plus 1. Otherwise, if it is the middle element is greater than key or equal to key, then the last will be revised to mid minus 1. We will keep on doing this until one of the two conditions become true. That is, first is greater than last. It means that the lower bound has crossed, the lower index has crossed the upper index. If this condition become true, or if we found the key is equal to the middle element, in both of these conditions, if any of these two conditions become true, the loop will be terminated. So if the loop is terminated, we will check that if key is equal to mid, then it is found and the index is set to mid. So found and index are actually two terms which represents the conditions, the information about the one of the two information, that whether it's found or not. If found is equal to found will contain the actual key element, and the index will define the location within the array or list where that key exists. So graphically, I can represent this whole idea. Here we have a list of alphabets A, B, D, F, G, J, K, M, etc. represented in the pink boxes. You can see that all these are in a sorted form. Then we are using 3 cursors. One for will be pointing to the first, another will be pointing to the last, another will be pointing to the mid. And to the left side we have labels first, last, middle, list, and key. For during every iteration, these different you can say labels will be updated. So initially you can see that first, last, we don't have any values for them, but key is defined as P. So within this binary search, our target is to find a key element that is P using a binary search. So the first step would be to initialize the first, last, and mid cursor. So the first arrow will be pointing to A, last is pointing to R, and mid of this data is pointing to J. This is the mid. So we will initialize based on the green data and the arrows given to the different bounds. We will define these labels. The first is actually at index 1, the last is at index 11. So first plus last divided by 2 is actually 11 plus 1 divided by 2, which is 6. So the mid is pointing to the 6th element. the content within the mid element is j, and the key which we are finding is p. Is the j is not equal to p, it means it's not equal to the j is not equal to key, and we can say that we can see that j is actually greater than j is actually less than p. If you consider a b c d in a sequence form, and if you consider a is less than b, b is less than c in such type of form, then of course you can, it's clear that p is greater than the middle element, that is j. So you can see that p can only be found after j. So we need to consider the, if we consider this whole data with reference to mid, we are 100% sure that if we can never ever find it to the left side of the mid, it will always exist to the right side of the mid. So now we have to revise the bounds, and we will move to the right half of this list. So as you can see that you will see within the next steps as well, and it's clear from here as well and from the discussion, that using binary search actually we are subdividing the existing list into two halves, that is the left and right halves. So we have a left half and then we have a right half. So that's why it is named as binary search. It is dividing it into two parts, and one of the two parts is considered in the next step. Here in this step we will consider the right half. We have to revise the bounds. So the first will be mid plus 1, that is k. The last will be as it is, and the mid will be actually first plus last divided by 2. Here the first is 7 at index 7, last is at index 11. 7 plus 11 is 18, divided by 2 is equal to 9, and at the mid the existing element is O, and the key is that we are searching is P. The key that we are searching is P. So P is not equal to O, and of course the key is greater than the middle element, that is O. So again we have to consider the right sub half in order to find the key. So again we will move on to the next step of the loop. We have to revise the first, mid and last. So the first will be moved to mid plus 1, that is P. Last will be as it is. So the first is at index 10, last it is at index 11. 10 plus 11 divided by 2, and if we round it up it will become 10. So the mid will be pointing to P as well, and the element that we have at the mid is actually P, and the key is also P. So it means that we have found the key. So we have found the key. So that's it. So these were the different steps that we perform. Now let's try again the same algorithm. We have the same data, but the only difference here is the key is equal to E, not P, it's E. So we will follow the similar pattern. We have to define the bounds first, last, and mid. First is 1, last is 11, mid is 11 plus 1 divided by 2, which is 6, and the element at the mid is J. We are searching for E. E is less than J, so we have to move to the left half by revising the bounds. So the first will become 1 as it was previously, and we have only changed the last. The last is shifted from 11 to 5, and 5 plus 1, first plus last is 5 plus 1, which is 6 divided by 2 is 3, so mid will become 3, and the element at the mid is D. So if we compare it with the key which is E, it's not equal, and also D is less than E. So we will move to the right half of this green list. So again, first will become 4, last will be the as it was previously, that is 5, mid will be 4 plus 5 divided by 2. If we round it, we will get 4, and the element at the middle is F, and the key we are searching is E, which is not equal to F is not equal to E. So the middle element is not equal to E. Now we will move on to the next step, that is to revise the bounds again, and we know that F is actually greater than the key element E. So if it is greater, it means we have to consider the left half. So for that case, we will change last to mid minus 1. So mid minus mid first will be as it is, and mid is mid minus 1, which is 4 minus 1, will become 3. So now you can see that first index is 4 and the last index is 3. So last is becoming less than first. So that is the stopping criteria. So we have to stop now. So it means we have searched all the element, and the element that we are searching for, that is E, doesn't exist actually. So this is the another condition through which our program an array of element, that is S, to the binary search function. We'll pass, of course, the key to the function that we are going to search within the list, and we'll define its lower and upper bound of the data. So we have lower bound, we have upper bound, but we don't have the mid bound. So in order to find the mid, first we have to check the condition that if lower bound is greater than the upper bound, it means okay, that is the terminating condition, we have to stop. Otherwise we have to find the mid by using this function, this equation, low plus high divided by 2. Mid will be initialized. Now element at the mid position will be compared with the key. If key is found at the mid, then we have to return mid index. That is the stopping criteria of this function. So if it's not, if S mid is greater than key, then we have to recursively call the same binary function but with a different bounds. So if mid is greater than key, it means the key can be found at the left sublist. So for that case, the low will be unchanged. However, the high will become mid minus 1. While if this condition is false, then it means that its mid is actually less than or equal to key, and then in that case we have to call again recursively the same function, but the bounds will be changed to the right side. It means that the low will become mid plus 1 and the high will be unchanged. So this is actually a recursive function which will keep on calling itself until this terminating condition is one of the two terminating condition becomes true. One of the terminating condition is if low is greater than high becomes true, then it will be terminated and it will return -1. -1 will be a signal that the element is not found. We have all searched through all the elements. Another terminating condition is that the element at the mid is equal to key. It means we have found the key. In that case, we have to return the index of the mid element which will of course be not equal to -1. L will be representing the index containing the key element within the list. So that's all for today. Thank you very much.